What is the core problem addressed in the paper related to large language models, LLMs?
The core problem addressed in the paper related to large language models, LLMs, is the detection and mitigation of hallucinations in LLM-generated content. Hallucinations refer to non-factual, arbitrary content generated by LLMs, which can be harmful in critical domains where accuracy is paramount. The paper focuses on developing a cost-effective and reliable method, semantic entropy probes, SEPs, to detect hallucinations in LLMs. SEPs are linear probes trained on the hidden states of LLMs to capture semantic entropy, which is a measure of uncertainty in semantic space. The key challenge addressed is to ensure the safe deployment of LLM-based systems by detecting and preventing hallucinations without the need for expensive and time-consuming methods like sampling-based approaches. SEPs offer a practical solution by leveraging hidden states to predict semantic uncertainty and detect hallucinations effectively. The paper highlights the importance of trust and reliability in LLM outputs, especially in high-stakes domains such as medicine, journalism, and legal services, where hallucinations can have serious consequences.
How does the proposed semantic entropy probes, SEPs method work? Illustrate step by step.
The proposed semantic entropy probes, SEPs method works by training linear probes on the hidden states of large language models, LLMs, to capture semantic entropy. The process involves several steps. 1. Training data generation. SEPs are trained using a dataset of hidden state, semantic entropy pairs. For each input query, high-likelihood model responses are generated via greedy sampling, and the hidden state at a specific layer and token position is stored. 2. Semantic entropy calculation. Semantic entropy, which aggregates token-level uncertainties across clusters of equivalent semantic meaning, is calculated. This is crucial, as it serves as the supervisory signal to train the hidden state SEP probes. 3. Binarization. The real-valued semantic entropy scores are converted into binary labels, indicating whether semantic entropy is high or low. This conversion allows for training a logistic regression classifier to predict these binary labels. 4. Training of SEPs. SEPs are constructed as linear logistic regression models trained on the hidden states of LLMs to predict semantic entropy. The probes are trained to predict whether a model generation for a given input query has high semantic entropy. 5. Probing locations. Hidden states are collected across all layers of the LLM to investigate which layers best capture semantic entropy. 2 token positions are considered: the hidden state at the last token of the input, TBG, and the last token of the model response, SLT. 6. Evaluation. SEPs are evaluated in terms of their ability to capture semantic entropy and predict model hallucinations. The performance is assessed using the area under the receiver operating characteristic curve, AUROC, with gold labels given by binarized semantic entropy or model accuracy. In summary, SEPs provide a cost-effective and reliable method for uncertainty quantification in LLMs by leveraging hidden states to capture semantic entropy without the need for multiple model generations, making them a practical solution for detecting hallucinations in LLM-based systems.
What are the advantages of using SEPs over traditional sampling-based approaches for hallucination detection in LLMs?
The advantages of using semantic entropy probes, SEPs, over traditional sampling-based approaches for hallucination detection in large language models, LLMs, are as follows. 1. Cost-effectiveness. SEPs are more cost-effective as they do not require multiple model generations for each input query, unlike traditional sampling-based approaches which typically require between 5 and 10 generations. This significantly reduces the computational overhead and makes SEPs more practical for deployment in real-world scenarios. 2. Efficiency. SEPs act directly on the hidden states of a single model generation and do not require sampling multiple responses at test time. This streamlines the detection process and makes it more efficient compared to traditional sampling-based methods. 3. Ease of training. SEPs are easy to train as they are constructed as linear logistic regression models trained on the hidden states of LLMs to predict semantic entropy. This simplicity in training makes SEPs more accessible and straightforward to implement. 4. Reliability. SEPs have been shown to be reliable in capturing semantic entropy and predicting hallucinations, even without the need for ground truth accuracy labels. This reliability makes SEPs a robust method for detecting hallucinations in LLMs. 5. Generalization. SEPs demonstrate better generalization to new tasks compared to traditional accuracy probes. They are able to predict hallucinations effectively across various tasks, models, and layers, showcasing their ability to adapt to unseen scenarios. 6. No ground truth required. SEPs do not rely on ground truth accuracy labels for training, unlike traditional accuracy probes. This makes SEPs more versatile and applicable in situations where obtaining labeled training data may be challenging or expensive. 7. Single forward pass. SEPs can capture semantic uncertainty even before generating the output, allowing for uncertainty quantification with a single forward pass through the model. This feature enhances the practicality and speed of using SEPs for hallucination detection. 8. Better performance. SEPs have shown to outperform accuracy probes in generalization settings, indicating their superior performance in detecting hallucinations across different tasks and models. 9. Scalability. SEPs can be scaled effectively to handle a wide range of tasks and models, making them a scalable solution for hallucination detection in LLMs. 10. Insights into model behavior. SEPs provide insights into the inner workings of LLMs by capturing semantic uncertainty encoded in the hidden states, offering a deeper understanding of how these models generate responses.
How are the SEPs trained, and what type of data is used for training them?
The semantic entropy probes, SEPs, are trained as linear logistic regression models on the hidden states of large language models, LLMs, to capture semantic entropy. The training data for SEPs consists of pairs of hidden states and semantic entropy values. Specifically, for each input query, a high likelihood model response is generated via greedy sampling, and the hidden state at a particular layer and token position is stored. Additionally, multiple responses, typically 10, are sampled from the model at high temperature, and the semantic entropy is computed based on these samples. The training dataset for SEPs includes these pairs of hidden states and the corresponding semantic entropy values. The input queries for training SEPs are derived from popular question-answering datasets, such as Trivia QA, Squad, BioASQ, and NQ Open. It is important to note that the training of SEPs does not require ground truth labels for model correctness or accuracy. Instead, SEPs are trained on the hidden states of LLMs to predict semantic entropy, making them a cost-effective and reliable method for uncertainty quantification in LLMs.
What are the main results and insights obtained from the evaluation of SEPs in both in-distribution and generalization settings?
The main results and insights obtained from the evaluation of semantic entropy probes, SEPs, in both in-distribution and generalization settings are as follows. 1. In the in-distribution setting, SEPs perform commendably, capturing truthfulness without the need for ground truth answers or accuracy labels. They are shown to be one of the best unsupervised methods for hallucination detection, even outperforming other unsupervised methods for truthfulness prediction. 2. SEPs show their true strength in the generalization setting, where they consistently outperform accuracy probes across various layers and tasks for short-form generations. They demonstrate better generalization to unseen tasks compared to accuracy probes, with a particularly large difference in performance observed for the BioASQ dataset. 3. When evaluating probe generalization to new tasks in a leave-one-out fashion, SEPs consistently outperform accuracy probes across different layers and tasks for short-form generations. This highlights the robustness and effectiveness of SEPs in handling novel tasks and scenarios. 4. SEPs are shown to be a cost-effective method for uncertainty quantification in large language models, LLMs, especially when the distribution of the query data is unknown. They operate on single model generations, unlike other baselines such as sampling-based semantic entropy, naive entropy, and p-true methods, which require multiple model generations, resulting in significantly higher costs. 5. The results indicate that SEPs are a reliable and efficient solution for detecting hallucinations in LLMs, offering a balance between performance and practicality in real-world deployment scenarios.
What are the limitations mentioned in the paper regarding the proposed semantic entropy probes, SEPs method?
The limitations mentioned in the paper regarding the proposed semantic entropy probes, SEPs method, include the high computational cost associated with semantic entropy estimation, which may restrict its use to critical scenarios. The paper acknowledges that SEPs are computationally efficient and reliable for uncertainty quantification in LLMs, but it also highlights the need for more cost-effective methods for hallucination detection. Additionally, the paper discusses the challenge of training SEPs on hidden states of LLMs without access to ground truth labels, which can be expensive to curate. Another limitation mentioned is that SEPs, while effective at detecting semantic entropy, may not match the performance of more expensive sampling-based methods in certain experiments. Furthermore, the paper notes that SEPs may not fully capture the complexity of semantic uncertainty in all scenarios, especially when compared to more elaborate methods that involve multiple model generations. Overall, while SEPs offer a practical and efficient solution for uncertainty quantification in LLMs, the paper acknowledges that there are still some limitations in terms of performance and scalability in certain contexts.